Okay, so I would like to introduce our first speaker for this session. This is Andy Ruina from Cornell University.
Recently asked me a question, and I thought I would ask the question again, maybe partially answer it, which is why is it that passive dynamics models tend to be complicated while controlled models tend to be simple? So my concern here is with stability. I don't know how much what I say generalizes to control problems in general. I just haven't thought about it yet. And by stability, I mean not being very close to a fixed point or a limit cycle, but not falling down. And the claim is that the same story holds for bicycles and walking, which has to do with the narrowness of my vision, perhaps, but I see these as sort of the same problem. A second way you can look at things, dividing the world up, is passive versus control, which is in the title. And then the third way you can think about it is simple versus complex. So there is this eightfold way of looking at things. You can look at bicycles versus walking and perhaps other models, but these are the two I'm going to talk about. You can talk about passive versus controlled, and then you can talk about simple versus complex. So these are these 8 different things we can look at and compare. But since I say that the story is the same for bicycles as for walking, we can just understand the story for bicycles and then see if the same holds for walking. So just look at the bicycle case, and we have these, we can look at passive versus controlled, and we can look at complex versus simple models. And I think that while bicycles are the same as walking, I don't think passive and controlled are separable variables in terms of this eightfold division of things. So we can compare bicycles and walking and limit ourselves to just bicycles. Okay, so my claim is on this slide is that where bicycles and walking were parallel worlds, passive and controlled are not parallel worlds. And so we go from here to here is different in this world than going from here to here in that world. And I'm just going to do that a little bit by example. So to start with, bicycles can balance themselves. And the soundtrack here is irrelevant. If you could make the sound low, I don't need sound for anything. So bicycles can balance themselves. We want to try to understand that. You can look at them in slow motion. And in slow motion, you see that if they're disturbed, they asymptotically come back to their straight ahead position, or at least some bicycles do. And how can we understand that? Well, a lot of people have worked on this problem, and I've talked about that before at this conference. The way people understand it is in terms of a complicated model. Here is a drawing from the book of Mimark and Fufiab, which has one of these complicated models, and we use a similar model. And it's complicated in the following way. It has 4 objects moving in 3 dimensions. It's got 2 control variables, and it's got about 25 mass and geometry properties, which you can reduce to maybe 17 by using dimensionless variables and combining terms and so on. Now, just as far as complicated versus simple, there's some sub-community of people here who are very computational. And simple means that they can write an algorithm that converges in polynomial time. And I do not mean that simple. I mean simple that it looks simple, like it's comprehensible by a human being. Okay, and by complicated, I mean things that look like this, which are simple in the world of these computational people, because at least here we can write the equations on a page or 2, whereas they're talking about systems where you can't write the equations in 1,000 pages, perhaps. So here's what the equations look like for a bicycle. If you have the linear equations, you can group them together and get these matrices, but each of these matrices is full of coefficients, which are complicated combinations of various parameters. If you take that, then you can do this complicated calculation. And again, this is not complicated in the computational world, but it's complicated in the intuitive world. To figure out whether a bicycle balances itself, you've got to look at the roots of a 4th order polynomial. And the equation for the roots of a 4th order polynomial is pages and pages long. Probably none of you have ever even seen that formula. You can get Mathematica to spit it out if you try, but it's a huge formula. And in that case, that just has simple coefficients. Each of the coefficients in that formula itself is a complicated formula. But if you don't usually evaluate it that way. If you evaluate it, you can draw these plots which have eigenvalues and the speed of a bicycle, and the dark lines being less than 0, since the real parts of the eigenvalues are less than 0. And it turns out for a bicycle with this complicated model, there's a region where the bicycle can balance itself from this complicated calculation. So you'd think, oh, we want to understand things in a simple way. Can we make a simple model of a bicycle balance? So there's a class of simple models of, oh, my model is that it's a gyroscopic effect. That's 5 minutes. Or it's a trail or caster effect, or it's just like a grocery cart. These are simple models, but they don't have predictive value. They explain something, or maybe they don't. We've written papers about how these particular things are wrong, but it doesn't matter. They're simple models that don't have predictive value. They don't tell you which bicycle is stable or not stable or so on. There's another whole approach you can take, which is to take that full model and say, well, how simple a system can we make that balances? And here is a bicycle. You take the wheels and turn them into skates, and you can balance this thing. And then you get a simple model that balances, but it's not the original bicycle. So it has some features, it's much simpler, and it has some features of the original bicycle, but it's not predictive in terms of what it does for the bicycle, and it's not so simple. It's still fourth order differential equations. To understand it, you still have to find the roots of a fourth order polynomial. It's just the terms in that polynomial are a little simpler. So is there a simple model for passive dynamics of a bicycle? And I think the simple answer is no, there is not. Okay, there's no simple predictive model of bicycle passive dynamics. Now you could say it's a simple model, it's 4 rigid bodies, that's not so complicated. Computationally, for certain people in this audience, that's not so complicated, but intuitively it is very complicated. How's it go for walking? We take the McGear walker, and that walks pretty well, and you want to understand that. Well, years ago when I used to talk about this, I'd show the equations to be very proud of the complicated equations we dealt with. If any of you half of you probably have written these equations, it's a complicated mess. How about take this thing, this guy. It's interesting. This guy can balance, but it can't stand up, and you try to figure out, can we get an intuitive feel for that and get some simple model of that? Well, I think you cannot. You can ask the question, is there a simple model for this? No one has found such a thing. Here's a nice simple model, which you can use as a metaphor for passive dynamics, but it's not a predictive model for passive dynamics. It has some features of passive dynamic walking, but you can't predict any details about what particular physical object will be stable or not stable, or how stable or unstable it is. You can say things like, oh, it's energy dissipation, or oh, it's a rolling egg, like you can about the bicycle, oh, it's a gyroscopic effect. That kind of model is qualitative. It might have some content, but it doesn't tell you anything. Or you can make a model like the simplest Walker model, and two things. It's only a metaphor, and it's not predictive. What about for control of a bicycle? So switch now to the controlled world. Here's a simple model of a bicycle. A bicycle is a point mass. That's it. And the wheels are skates. And all the geometry is vertical. It's got next to no parameters in it. Here's what the equations look like. These little marks are time derivatives. Very simple second order differential equation. You take this, and on the computer, you design a controller, and students in my lab have done this, and they've written a bunch of controllers based on this model, optimized in the computer, or LQR with this computer, with this model, or taking motor constraints into account or not, and they've gotten lots of different controllers which work fine, not post-tuned. In other words, this is a good model for designing control of this bicycle, which is in no way simpler than any other bicycle. This first new video I showed. Okay, so you can make a good controller with this bicycle with a point mass model. Now, people have not yet done that with walking, but I think they will. So here's this complicated model on the left, good for passive dynamics. Here's this simple model on the right, and it's way simpler. Why does the simple model work here? And there are a few reasons. One is that if you have a strong enough motor, which most of us do in most of our thinking, you can kill 1 degree of freedom of the model. So that rather than have 2 degrees of freedom, leaning and steering, the controller operates on steering, and the steering, rather than being a controlled variable, becomes a control variable. That is, you have a simple controller that takes care of the steering. You've reduced it from a fourth order system to a second order system. And then you only have 1 degree of freedom, and then for these kinds of systems, that 1 degree of freedom is simple. What if you add to the bicycle lots of other degrees of freedom? You say, oh, real bicycles are complicated, they have humans on them, and they lean, and so on. It's my belief, and this is not tested, but we could test it in simulation, that this model will still be good. All those extra degrees of freedom can not help you balance much, and they can't hurt your balance much, and we will still be able to balance the model, a bicycle, using this model. What about walking? How is walking the same as bicycling? Well, I believe walking balance is low-dimensional like bicycle balance is. Bicycle balance is one-dimensional. Walking balance might be three-dimensional or two, depending on about whether you're worried about steering as well as falling frontwards and sideways. But there's this common feature that you only have to worry about simple things, the simple pendulum things. Maybe you don't model it with a simple pendulum, but it's the simple pendulum things. It's the uncontrolled degrees of freedom. All the controls that you have only have influence over balance by how they affect where the force interacts with the ground and how hard you push on the ground. In bicycle, there's no how hard you push term, but in walking there is. There's push off, which is used for balance. All the other things, all the upper body distortions, swinging your legs around, bending your body, kicking with the other leg, don't help you much in balance, and they don't hurt you much in balance. Therefore, I think the same will hold for walking. It's not yet demonstrated because no one's made a good controller this way. But in the end, I think this is physics, not my worldview. That is, anybody here who makes a robot balance well, if you study it as a biologist and look at the mechanism of balance, you will find high correlations between simple components of the motion and simple components of the control, being foot placement and push off. Okay, balance versus passive versus controlled. Balance means keeping the center of mass above the contact. That's true whether you're doing passive or controlled. Whether you're doing passive or controlled, the balance is achieved by manipulating the contact location or pushing off. In passive, you have more degrees of freedom. In controlled, you kill those degrees of freedom by using the control on the easy to control degrees of freedom. In passive, all the coupling is important. In a controlled situation, you've got rid of the coupling because you're controlling, for example, the steering degree of freedom or where the foot is in swing phase. In a controlled situation, you're using a computer as a computer. In the passive situation, all of that complication is needed because all of the weird coupling, all the moments of inertia coupling with the other moments of inertia and the gravity terms and so on are important because the mechanics is the computer. And you need that complexity just like you need all the lines of code in the control version. The passive one has limited versatility. The controlled one has lots of versatility. You can do anything you want with the motors. Let me just give my conclusion here. The passive one, the simple model, is a metaphor. In the controlled situation, I think the opposite is true. The high fidelity model is not needed. I think it could be a distraction. I think it can lead to overfitting in your control. So here, if you're doing passive, you can use the simple models as a metaphor, but they don't tell you anything. And in the controlled version, you can use the high fidelity model, but it might be overkill, overfitting, or distraction. So simple models are appropriate for control. Complicated models are needed for passive dynamics. Okay.
Questions?
Thank you.
I guess we switch out here. We should switch, right?
Yeah. Do you have a beef with simple models of passive dynamics for energetics? Like understanding of energetics as more than just a metaphor? It's primarily, your claims are primarily about stability, right?
Yeah, I've thought just a little bit about this grand question. And I think sort of my quick thoughts are that the simple models only give you sort of the right energetics once it's close to the optimum in lots of ways. That is, a complicated model has to be tuned up before the simple model is useful. And just to be more particular, if you do the kinds of things Manoj did with the particle in doing energetics with a point mass model of a person walking and running, that might be kind of in the neighborhood somehow once you know that the bad things aren't being done with all the complicated parts. So in other words, the energetics is different from stability in that all those parts can cause damage. They can't be particularly helpful, but they can cause damage. Where in the stability, they can't cause damage. So it's not the same situation with energetics as it is with stability. Did you understand that answer or no? Or did I address your question?
I think you're trying to address my question.
I'm just incoherent. The big thing is, in balance, you have lots of degrees of freedom. They can't help you much, and they can't hurt you much, so you can ignore them. In energetics, all those extra degrees of freedom can hurt you. If you manage to use them so they don't hurt you, I think simple models can tell you things about energetics. So, is that saying it slower work better? Manoj, you got some back there.
Yeah. So do you think that the simple model for the controlled side was predictive in terms of the region of attraction?
Yes.
And then the second would be, how much of the win for the controlled version?
I'm trying to make eye contact with somebody here.
Right here, Andy.
Okay.
How much of the difference do you think can be explained just by the controlled version giving you a larger basin of attraction, to being more robust to those sort of modeling errors you're talking about?
Okay. I think, let me just rephrase your question. The question is, if you had, for example, the best controller in the universe of a given robot that used all the degrees of freedom, how big is the basin of attraction for that versus the basin of attraction of that same robot controlled in, using a simple model?
No.
And it's certainly bigger, and you're asking about...
More that the difference between the controlled robot versus the passive robot. Right, so if the passive model is not predictive, is that just because its basin of attraction is very small, and so you have to be precise, and therefore the simple model fails?
The passive models are barely stable, that's correct. So it's sort of like if you're doing the controlled version, does it matter all the lines of code? Yes. There's all kinds of ways you can make a robot which can walk well walk badly by changing little lines of code. And there's all kinds of ways you can make a passive robot fall down by little changes in the model or little changes in the initial conditions and so on. So it barely works, just like code barely works. Like almost all variations of a computer code will make it fail. Does that address your question?
Sure.
Is it fair to say that you're assuming a particular kind of mass distribution for these objects?
Yes.
Like where they're top heavy, bottom light kind of thing?
I'm thinking about bicycles and bipedal robots and bipedal human beings and maybe birds. I don't know if these extend. I don't see how my thinking is too narrow to think about quadrupeds or anything else. So when I have my general thing about simple versus complicated is about top-heavy things with a small contact on the ground. I mean, maybe there's some kind of generalization to, maybe there's a deeper thing I'm saying, but I haven't thought about it to say that it's a deep thing. Does that address your question? What he's trying to say is I should have said, I'm only talking about walking robots and that exist, that are bipedal and bicycles and nothing else.
I also think that you have to have, for this sort of, using simple models to design simple controllers, in the two cases that you've given, you're going to reduce yourself to having a small number of things that you can change and a small number of output things that you can watch. And then I agree, it's easy to make controllers for that. But as soon as you give yourself a couple of extra degrees of freedom in your joints, knowing what to do with those excess degrees of freedom becomes the hard problem. So if you're going to limit yourself to a bipedal robot that has sort of just barely enough degrees of freedom to do the task of walking with maybe 1 degree of freedom or 2 degrees of freedom left over, then I would agree that using really simple models can give you a framework for doing really simple.
How much time do I have to answer that question? Okay. Okay, so the point of my talk is that you are wrong in what you're saying. Okay, so the idea is...
And I completely disagree.
I rest my case. All those extra degrees of freedom, when you control your robot, you have to figure out what to do with them because they're there. And those extra degrees of freedom can make your robot fail various ways. Like if you don't pay attention to them, the right leg will trip on the left leg, or it will trip on the ground, or there'll be the sudden ground reaction force and it will hop in the air. So there are lots of ways you can fail besides simple balance failures. But if you say, overall, we're interested in the balance problem, all those extra degrees of freedom are of absolutely, no, that's what I was going to say. All those extra degrees of freedom are of very small use, no matter what you do with them.
I agree. No, that I agree with.
And so that they all reduce...
But Andy, that's not a hard control problem. I mean, that's right.
The balance problem is not a hard control problem. That's my point of my talk. The balance...
I don't disagree with that. But that's not what's hard about making robots that walk.
Well, I mean, there's an issue of what's hard about making robots walk. I think the primary thing that's hard for a crowd like this is systems engineering problems. Making there be no short circuits, no bugs in the code, the wire's not breaking. That's what's hard about robots, because we don't have multi-million-dollar budgets to debug all that stuff. After that, what's hard about making a robot walk is not, no one's convinced me that there's anything hard about it. We're just not good at it so far. Do you think there's something hard about it?
I think if you add enough degrees of freedom to make it do something other than walk in a straight line, all those extra degrees of freedom that can hurt you will, unless you do something smart.
Well, they will how, you know? So you have to worry about those things like kicking yourself and stuff like that, or making them able to do the things you want. You have all these degrees of freedom. You have to get your foot from here to there. But I think, you know, that's what I'd call robot arm problem, where you have actuators to match your degrees of freedom. So if the high-level balance controller gives all those things a robot arm problem, I think people are pretty good at solving the robot arm problems. Not that they're trivial, but there's a community of people that are good at those problems. Does that address your question?
Maybe. For now.
Okay. I just want to point out, there's a tall blonde guy who's in my lab who's not here today. He bought his ticket for the wrong day. Shows the general competence of my lab. And but he disagrees with me, so it's not like I've sold my case to everybody. You made it. Okay, he did make it. There he is. Will you vouch for the fact that you disagree with me? What? Absolutely. He absolutely disagrees with me. So.
Thank you. Yes, I followed your work long, even we talked in Michigan. I want to make passive stabilizing walking systems. I wonder, when you built the skate bicycle that we saw in the video, that was one of two possible permutations that you had in your paper. I wonder if you've built the second permutation since, which was very interesting to us for walking stability, and if you have any ideas on how to do one of these with walking, I'd be interested to hear them.
Okay, as far as the bicycle goes, me means Aaron Schwab in Holland and his students, and he built a couple, I don't know which one you're referring to, but he made a passively stable rear steering bicycle, just to violate another one of the myths about bicycles. But I don't know if that's the other one you're talking about. He did build that one.
Piggybacking on Noah's observation, if I care about a relatively small number of inputs and a relatively small number of outputs, and I'm thinking about a regulation problem, is what you're saying equivalent to the Kalman decomposition theorem for the linearization of your nonlinear system around your operating point? That there's a subsystem?
I think I can answer, but even though I don't understand a word that you said, I think I can say no, because the world of linear systems and so on is more complicated in a way, because you have all these degrees of freedom and you have all these actuators and you're trying to optimize things around a fixed operating point. And I'm interested in the large control authority issues. So anything about linear systems doesn't really quite apply to what I'm talking about.
I completely disagree.
Okay. No, do you actually completely disagree? I don't think when you're talking about linear systems that you get this decomposition unless you add extra things like that you're allowed to kill certain degrees of freedom, and that you choose a controller that's hierarchical, which you can choose to do, which is not what.
I'd say that your claim implies some, kind of. You have to get things right to first order in order to get things right to higher order. And so what you're saying in particular is true about the linearization, and it's the Kalman decomposition theorem.
Well, Kalman's very smart, so that's really nice. But you have to explain it to me.